Okay, so our last section this week is 11.3, and it's on the binomial theorem. So the binomial theorem, we're going to see come up a couple times. You can use the binomial theorem to do what we're going to do today, which is expand a binomial. You can also use it when you talk a little bit about probability and statistics. So we're going to see this again next week, because that's going to be our last unit. We're going to do a little bit on probability. So what I want to do is look at a few different series. Okay, I'm going to just expand a few special things out. This is a series because you're adding up all these terms. And the first one is a plus b squared. Okay, to get that, I would have to write a plus b times a plus b. And how would I do that out? Yeah, you would FOIL it or double distributive property. There's a times a, which is a squared. A times b, which is ab. Another a times b, so that's 2ab. And lastly, b times b is b squared. So now if I wanted to do a plus b cubed, what would I have to put onto the expression I just had? Another a plus b. Now I would FOIL the first two, get the answer, and then FOIL that answer by a plus b. And so very quickly this becomes time consuming. Okay, you end up with lots of multiplications and combining like terms. So I've already done it out for you. A plus b cubed. And my goal here is basically to look for a pattern. Okay, I want to try to find a pattern in this, about maybe 3 or 4 different things we're going to mention here, okay, that are going on. Okay, here's a plus b to the 4th. And I really think with just the first 3, you can probably start to see some kind of pattern or several patterns going on here. Okay, and this is a plus b to the 5th. Okay, you don't really need to copy down a plus b to the 5th. You could just look at it and see if we notice a pattern. Right, does anybody see a pattern? Any kind of pattern? Yep.
For the a's, they're always raised to the power that they're raised to first.
All right, so for the a, the first term in that expansion, the exponent is always the first term in the binomial to the power that it had originally. So a to the 4th, a cubed, a squared, and so on. And then what happens to the exponents on the a's from there?
It decreases.
Yeah, the exponent on the a goes down by 1 until it finally disappears. A cubed, a squared, a to the 1st, technically a to the 0, but that's just 1. So the exponents on the a's go down by 1. Yep.
It's the reverse for the b's.
Yep, and it's the reverse for the b's. You never see the b as the first term. Think of it as b to the 0. But then you have b to the 1, b to the 2, b to the 3, b to the 4th, b to the 5th. Okay? So the exponents on b go up by 1 till you get to the highest exponent, which is the exponent you started with. All right, does anybody see some other patterns? Yep. Tom?
The exponent comes before the a to the power, then b.
Can you say that again?
Just the second term in
The second term? Okay.
And the exponent is in front of that term. Like the 5
Yeah.
is the same as the exponent on the original equation. Like what's it equal to?
Oh yeah, that's a cool pattern. I never really noticed that, but he's just saying the number you see here and the number you see here always look like they're the same, and they are. 5, 5. Yep. Okay, not a pattern I was going to mention, but yep, looks like that always happens. How about if you add the exponents together on any term? They always equal what?
They always equal the exponent.
Yeah, they always equal the exponent. Okay. 5, 5. 4 and 1, 5. 3 and 2 is 5. 2 plus 3 is 5. 4 plus 1 is 5. 5 is 5. Okay, so yep, that's a pattern. And there's one more really important pattern. It's the hardest one, but it's probably one of the most important for writing these numbers out. Yep.
It's like a mirror image of the coefficients.
Yep, so you see a mirror image like 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. So you see like a mirror image.
It's that triangle.
Yes, these coefficients, 1, 3, 3, 1, those come from a row in Pascal's triangle. Okay. Another pattern I don't think anybody noticed is that when you expand it, you end up with n plus 1 terms. So if you square something, 1, 2, 3 terms. Raise something to the third power, 1, 2, 3, 4 terms. Okay? So you always get one more term than the exponent when you expand it. Okay? So that's a pattern. The sum of the exponents is n. Okay? We saw that with the 5. This pattern, I think we found, the degree of A starts at the highest and goes down. B starts at 0 and goes up by 1. Okay, till you reach the exponent that you're raising, till you get to your power on your binomial. And lastly, the important one, where are these coefficients coming from? Pascal's triangle. Okay, so we're going to use all these patterns when we expand out a binomial. We're not going to write out and FOIL all these things. All right, so let's take a look. A quick reminder about Pascal's triangle. Right, so Pascal's triangle starts with a 1, and we call that row 0. Okay, that's the one thing when we're counting today, using Pascal's triangle, we do have to start with the 0th row. Then we have the first row, second, third, fourth, fifth, and I did 6 rows. Each row starts and ends with a 1. Okay, so you kind of have 1s going down the sides of the triangle. And how do you generate the rows? Like if I wanted you to do another row, how do you figure out the numbers you should put in it? Yep, Corey?
Put a 1 on each end.
Yep, put a 1 on each end.
Then you just have the 2 terms above it.
Yeah. So the way we got this term was to add the 2 above it. 4 plus 6 gives me 10. Right? And you should probably know at least up to row 4. Okay, it's handy to at least memorize up to that row. And then if you really need more rows, you can write them out and figure out what they are. So each row begins and ends with a 1. Each entry is the sum of the 2 numbers above it. And as we already pointed out, the numbers in the nth row are the coefficients if you expand a plus b to the n. Right? So let's look at the last one, a plus b to the 5th. If I go to the 5th row in that chart, I should see 1, 5, 10, 10, 5, 1. Are those the numbers in row 5? Yeah. 1, 5, 10, 10, 5, 1. So between using the triangle and the patterns that we noticed, we're going to be able to expand something like a plus b to the 6th pretty quickly. Much quicker than you were able to do it with FOIL. So let's try this. What row should I be looking at in Pascal's triangle?
6.
Yep, row 6, starting with the 0th row. That's row 6. Okay, so what is my first coefficient going to be? Yep, it's going to be a 1. And now it's going to be what letter to what power?
A to the 6th.
A to the 6th. Do I see the b term?
No.
Nope, not yet.
Plus.
plus, what's my next coefficient?
6.
6.
A to the 5th B.
Yep, a to the 5th b. Okay, next term.
15 A to the 4th B squared.
A to the 4th b squared. Good, we're just going to follow this pattern. Next coefficient.
20 A to the 3rd B to the 5th.
A to the 3rd, b to the 3rd. Okay, somebody else give me the next term.
15 A to the 2nd B to the 4th.
Good, 15a to the 2nd, b to the 4th. Okay, next one, I'll do this one. It's going to be 6a, b to the 5th. And what about my last term?
B to the 6th.
Yep, you can put the 1. You don't have to put the 1, but it's 1b to the 6th. So very quickly, well, a lot quicker than I think you'd do the previous way, we just expanded a plus b to the 6th. Now, we didn't prove this theorem. Okay, all we did was notice a pattern, and we were extending it to a plus b to the 6th. Okay, proving that this actually is the answer without doing this out, proving this theorem in general, that's a little more work. Okay, which in this class we don't get into. Any question on that one? All right, let's try 2x plus y to the 4th. A little harder, so that's why this time I only did an exponent of 4. Okay, what row do we have to look at in Pascal's triangle? 4th row. So I'm going to go look at that, write it down. 1, 4, 6, 4, 1. Okay, so we'll put that up here. And now this time, this is A, and this is B. So what do you think I'm going to have to do as I write down the first term? Start with the coefficient. It's going to be 1. And how am I going to write a to the 4th? Because this time it's a little different.
Is it only 16x to the 4th?
Right? Can you explain like how you would write that down? We're going to do that out as our next step.
So you gotta do 2 to the 4th, x to the 4th?
Right. You have to do the 2 to the 4th and the x to the 4th. So we got to put it in parentheses. Okay, with the y, we really don't need to worry about parentheses, but with the 2x, you do. All right. Tom, what's my next term?
Would be 4, 2x to the 3rd y.
Yep. And again, we'll clean this up in the next step. Okay, Olivia, how about my next term?
6,
Yep.
2x, 2 second, y second,
Y the second. Okay, Maddie, how about my, what are we on, 4th term?
4 times 2x.
Yep, Y the 3rd. And DJ, my last term?
We will have y to the 4th.
Yep, just Y to the 4th. All right, now we need to do out what Corey had just done. So, the first one, we're going to raise the 2 to the 4th and the x to the 4th. What's 2 to the 4th? 16 times 1?
16.
Still 16. X to the 4th. Yep. Okay, next one. What's 2 cubed?
8.
So we have 8 times 4. 32. X to the 3rd. Y. Okay, next one. 2 squared
4.
times 6. So I get 24.
X squared. Y squared.
Yep, x squared, y squared. Okay. Someone give me the whole next term. 8x y cubed. Yep. And the last term, just y to the fourth. Okay. So on a problem like that, you do need to do out all the arithmetic. Okay? But there's your final answer. Notice we had a 4 as the exponent. You should have 5 terms in the final answer. 1, 2, 3, 4, 5. Okay, a little harder to see the pattern in the coefficients once you do out all the arithmetic. You could work backwards maybe if you had to, but that would be a little difficult to go back to what you had. Okay, questions on that one? All right, and let's try one more. 3x minus 2y cubed. Steph, what row in Pascal's triangle do I need to look at?
Third one.
Yep, third one. And Shelby, do you remember what the third row is in Pascal's triangle?
1, 3, 3, 1.
Yep, 1, 3, 3, 1. Now, before I do this out, okay, the pattern that I had was plus. Heaven, can you just shut that for me? The pattern was a plus and a plus. What do I have to do here to maybe think about writing this as a plus?
Plus
So 3x what?
plus negative 2.
Right. Plus negative 2y cubed. That's my A. That's my B. And now whether this negative is going to cancel, it's going to depend on the exponent. If it's even or if it's odd. So a lot of times when you have something with a minus, after we finish expanding it, you're going to see a pattern positive, negative, positive, negative. Okay? It's not going to just be positive, 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 positive. Okay? It's going to alternate. Okay. So who can give me my first term to expand that out?
Do it out completely, or just so you
No, we don't have to do it out completely. Just tell me before I do it out. Yep.
1 times 3x to the third.
Yep. 1 times 3x to the third. Okay. Plus, what about my next term? Go ahead, Brad.
3x squared, or 3 times, all 3 times.
Yep, 3 times 3x squared
Negative 2y.
times negative 2y, and that's just to the first. Okay. Somebody else give me my third term. Matthias?
3 times 3x times negative 2y squared.
Squared, good. And my last term. Go ahead. Yep.
Negative 2y cubed.
Yep, negative 2y cubed. Right, let's do everything out, see what we get. What do you get when you do out the first term?
9x cubed. Wait, no, that's not 27x.
27
X cubed.
x cubed.
And the next one is going to be
Before we even do it, do you think it's going to be a plus or a minus?
plus minus.
It's going to be a minus. Okay, now do it out. What's 3 squared? 9 times 3.
27.
And what's 27 times negative 2?
Negative 54.
Negative 54. And what's the rest of it?
X squared.
X squared y. All right. Now I told you the pattern, so what do you think the next term is going to be? It's going to be positive. What's negative 2 squared? 4 times 3?
12.
Times 3. Positive 36. X, y squared. And the last one? Negative 8y cubed. Okay. Any question on that? Yes?
How do you get 36?
36, you do negative 2 squared is 4. 4 times 3 is 12. 12 times 3 is 36. All right, so the last one, I'm not going to do out completely, But what would end up happening, I'll just show you the last term. It would be y squared cubed. Because your first one, you'd have your, ignoring the coefficients, you'd have your 2x cubed, no y. Then you'd have your 2x squared with a y, 2x with your y squared squared, and then lastly, you wouldn't have a 2x, and you'd have y squared cubed. How do you do this out?
Y squared.
So it's y to the 6th. And so when you have a power to a power, you, multiply them. Okay? Any questions on how you'd fully expand something like that? This would just be the last term. Okay. So Pascal's triangle. Can anybody think of what could become more difficult trying to continue using this triangle?
When you get past the rows you already created.
Yeah, if you want to do something like, let's say we want to do a plus b to the 15th. The a's and b's wouldn't be hard because you just decrease the exponents by 1 or increase them by 1, but the coefficients become more difficult. So we need a better way to get these coefficients. Okay. And that's what we're going to look at next. Okay. So as your power starts to get large, we're going to come up with a better way to calculate the coefficients. Okay. And that's what we're going to get into factorials. Okay, so a factorial, first of all, it's only defined for positive integers. There's no such thing as 3.2 factorial. You can do 3 factorial, you can do 4 factorial, but we're not going to do anything in between. We define the symbol n factorial as an n with an exclamation point. Or if you want to pronounce it, n. That's how you pronounce it. Either you can say n factorial or just get excited when you say n. Okay, so n factorial basically means to multiply every number from 1 up to n. Or you could say from n down to 1. Okay, so n is the product of every integer from 1 to n. So for example, 4 factorial means 1 times 2 times 3 times 4. It's kind of like what we did with summation. Okay, when we said we're going to add all the numbers from 1 to n, well, now we're multiplying all the numbers from 1 to n. And there's actually a symbol in math that means the same thing as sigma, except it means multiply instead. If you wrote this, that is how you write a factorial in a sigma-like notation. You don't use the Greek letter sigma, though. You use the Greek letter capital pi. And what this means is you're not adding things up, you're multiplying things together. But it works exactly the same way as a sigma. You just change all the plus signs to multiply signs. Okay? We're not going to study this symbol. We don't get into this.
So one of my middle school teachers always got mad when I didn't do like the squiggly lines for pi.
Oh, maybe, I don't know. Yeah, this squiggle means it's like a lowercase. That's a capital, but yeah. Most people, when they're like in geometry, if you use pi a lot, I wouldn't be very particular how you write the pi. It'd be fine.
You have to have an exact stencil.
Right, so the first couple are a little strange, like 0 factorial. Anybody have a guess what that one is?
1.
Yeah, it does turn out to be 1. Okay, and the way you do it is 0, go to math, go to probability.
I apologize for the interruption.
All right, so after you go to math, go to probability, go to the 4th option down, that's where your factorial is. Yeah, so 0 factorial is 1. Okay, how about 1?
It's just 1.
Yeah, 1 is, it's just 1.
Does that mean 0 and 1 are equal to each other?
It means yes, 0 and 1 are equal to each other. How about 2 factorial? Yep, that would be 2 times 1, or 2. How about 3 factorial? 3 times 2 times 1, which is 6. 4 factorial,
12.
24.
24. 4 times 3 times 2. And what about 5 factorial?
52.
52.
Like she said.
120.
Oh,
5 times 4 times 3 times 2.
yeah. No, I was way.
Okay, so factorial, it's not a continuous function because we only define it over the integers. You can try typing in like 3.5 factorial, and I think you'll get an answer. It goes beyond what we're studying. But you can type in, well, that doesn't really make sense with the definition I gave you. Okay, so we don't really look at decimal factorials in this class. Okay, any question on how to calculate a factorial? Because this is what's going to replace Pascal's triangle. Okay, this idea of factorials. Right, so suppose you want to find the number in row n, column r of Pascal's triangle. Okay, remember, anytime you're doing counting in the triangle, you always start with row what? 0. And what column do you think you'll start with?
So you have columns in a triangle.
You just count left to right.
Does it like zigzag that?
Well, yeah, the columns might not line up perfectly, but you just look at like whatever row you're in, you count across that row. Those are your columns. So we start with row 0. I want to start with column 0. Okay. Yep. So if I were to go back to the triangle, this would be row 6, column 2. 0, 1, 2. Okay? So that's how you count. And the notation we're going to use, instead of writing out row 6, column 2, we would write something like this. That means row 6, column 2 in Pascal's triangle. Okay, another way you can pronounce this is 6 choose 2. Or, if you're using n and r just generically, n choose r. Does anybody know where this notation comes from? N choose r? Okay, this comes from statistics. Okay, if I had 4 objects and I wanted to choose 3 of them, okay, that's what this represents. Okay, so there are 4 ways you could pick 3 of these objects. Right? You could pick, green, black, and red. You could pick red, blue, and black. You could pick, you do them all out. There's 4 different combinations. Right? So that's what it means. So basically what we're calculating in this case was if you had 6 people, how many different ways could you pair them up? And the order of the pairing doesn't matter. Pairing Corey with Tom, Tom with Corey, it's the same pairing of people. Right? So if I wanted to know how many ways can I pair people up in here, it would be 13 choose 2 for the full class when everyone's here. It's 13 people. How many ways can I pick 2 at a time to pair them up? And we could figure that out if we wanted to. It's probably pretty good size. But. Okay, so we have a notation to write what we're looking for. N choose R, row, column. But we still don't have a way to figure this out. Okay, so next I'm going to show you the formula for N choose R. Okay, so your formula for N choose R is N factorial over N minus R factorial, R factorial. Now, the problem with factorials is they get very, very big very quickly. So let's say I just tried to type in 15 factorial. Any guess how big that might be? 10,000s, 100,000s, millions?
200,000.
So in the hundreds of thousands? It's a little bigger, yeah. It's 12 digits long. So now we're getting into the, billions? I think that's in the billions. by the time you get to like 80 factorial,
Why can't you do it on the calculator?
yeah, it might just say overflow, because now the calculator can only go up to scientific notation where the exponent would be 99.
Wow.
Okay? So 80 isn't even that big of a number, but you can't even do 80 factorial. So when we start to deal with this formula, we need an efficient way to do this. Sometimes the numbers are too big. Can't even type them in. But I'll show you a way that you'll probably be able to do most factorials in your head. All right, so here's Pascal's triangle written out using n choose r notation. I've replaced all the coefficients with our notation. Row 0, column 0. Row 1, column 0. Row 1, column 1. Row 2, column 0. Row 2, column 1. Row 2, column 2. If you plugged in the n and the r, this is n, that's r, into this above formula, you would get all the numbers that we've already generated. Okay, and you're not going to have to do out an entire row of Pascal's triangle when it starts to get really big. Okay, I would never ask you to do out the entire, say, 20th row of Pascal's triangle. I'll show you a test type question that I would ask you. Okay, so there's your Pascal's triangle written with n choose r notation. And here's the binomial theorem written out following the patterns we've already seen. Okay, it looks a little confusing, but if you break it down, it's not bad. Okay, you start with a to your highest exponent, and then the a exponent drops by 1. Decrease it by 1, decrease it by 2. Keep decreasing it until the exponent on a becomes a 1, and then it finally disappears. Okay, exponent on b. It's not present in the first term. Then you've got b to the first, then you've got b to the second, and b keeps increasing till you finally get to b with the highest exponent. Okay, then your coefficients, that's what we just talked about. If you're expanding a binomial to the nth power, you're going to look in row n. The first one is going to be column 0. Then you're going to go row n, column 1. Row n, column 2. Row n, column 3, till you finally get all the way as far over as you can go in that row, and then you're done. Row n, column n. That's the end. Okay. The kind of problem I would ask you for is if I said, let's expand out a plus b to the 15th power. Try one like this at the end. I would probably say, just give me the 12th term. You don't have to do every term. I just want to know what the 12th term would be. I want the coefficient, the power on the a, and the power on the b. If this exponent was smaller, if it was like a 5 or a 6, then I would probably say do the whole thing out. I want the full expansion, just like we did at the beginning. So we'll do one in a little bit. Any questions on the binomial theorem? All right, so let's try just calculating some of these. Okay, let's practice that. So this is the number that would be row 6, column 4. This one I think we did. I think we did Pascal's triangle out to row 6. So I'm going to go back and look at it, see what the answer should be, and then we'll do it out. What is it? Row 6, column 4. So row 6, 0, 1, 2, 3, 4. So when we're done, we should get 15. Okay, let's see if we do. All right, what goes on the top of the fraction?
N.
Yep, n factorial, which in this case is 6 factorial And what goes on the bottom?
6. Yeah, 6 minus r.
Which
Which
is
is
4
4.
factorial. And something else.
R factorial.
R factorial, which is 4. Okay, and if you've seen this before, someone in the last class said, isn't this the formula for doing what's called a combination? It is. It's the formula for a combination in probability. All right. So top, if I write out 6 factorial, what does that mean?
6 times 5, that's 4, 3, 2.
Yep, 6, 5, 4, 3, 2. And what's 6 minus 4? And what's 2 factorial? Yeah, just 2. And 4 factorial is 4 times 3 times 2. Before I type this in, because the numbers can get pretty big, let's cancel out what we can. What cancels out?
2s, the 3s, and 4s.
The 2s, the 3s, and the 4s. Since we're always going to have a big chunk of it cancel out like that, I'm not going to write the whole thing in the future. Okay, we'll cancel out the big chunk first. And now we're just left with
30 divided by 2.
30, 6 times 5 is 30, divided by 2 is 15, which is exactly what we should get. Right? Let's try to find the number in the 9th row, 5th column. Okay, what's going to go on top?
9.
Yep, 9 factorial. So we're going to have 9 times 8 times 7. Well, let me write it out. And how about on the bottom?
9 minus 5 factorial.
Which is
4 factorial.
4 factorial
5 factorial.
times 5 factorial.
That would have been embarrassing.
Now, I want to cancel out the biggest chunk here that I can. So look for the biggest number on the bottom. Look in the top. The top would be 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1.
9 times 8 times 7 times 6, then, right?
Right. We could just do 9 times 8 times 7 times 6 because we have a times 5, 4, 3, 2, 1 in the top and a 5, 4, 3, 2, 1 in the bottom. So any questions on that chunk that just canceled out?
And then you just have 4, 3, 2, 1.
And now I just have 4, 3, 2 on the bottom. Now what's nice is this always has to reduce so the denominator comes out to 1. You'd never get a decimal when you do a factorial. Okay, because you're always multiplying integers. So you can reduce any way you want. So what could I reduce here?
8.
Okay, 4 goes into 8 twice. What could I reduce now?
With the 2 2s.
Yeah, we could do the 2 with the 2.
All right. The 3 and the 6.
And you could do the 3 into the 6. So you're left with 9 times 7 times 2. Right, so if you're not sure, just type it in. 9 times 7 times 2, 126. So that should be the number in row 9, column 5, Pascal's triangle. Or another way of thinking about it, if you had 9 people, how many ways can you pick 5 people out of the 9 to make a group? There's 126 ways to do it. Okay, any questions on that?
So this is going to be like stats kind of thing?
You use a lot of this stuff in stats, but we're really using it to expand a binomial. But a lot of it overlaps. Yep. All right, so this one, I don't want you to expand the whole thing. I want to know one term out of the whole thing. I want the 12th term. If you were to expand this out, how many terms would it have? 16. It always has one more than the exponent. So if you did the whole thing out, there's 16 terms. I draw this little diagram just because it kind of helps me to keep track of things rather than trying to do it all in my head. And now I want the 12th term, starting with what term? 0th term. So this is 0th term. 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th. I want that term right there. All right. So now let's start with our coefficient. What row of Pascal's triangle am I in? Row 15. Just look at your exponent. And what column? I'm in the 12th column. Definitely something you probably wouldn't have written out. Okay, you're not going to have 15 rows of Pascal's triangle, so you're going to need that formula. Now I want to figure out 2x to what power, 3y to what power. What would the power on the 2x be for the 0th term? 15. And then what would it be on the first term? 14. And then 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3. So 2x cubed. And now we know the pattern, the exponents have to add up to what number?
15.
So what's the exponent on 3y?
Well,
Oh. That's our answer not done out. Okay. Now we'll do this out. How do we do out 15 choose 12?
15 factorial over 3 factorial.
Yep.
12 factorial.
Okay, big chunk of this is going to cancel. We'll do that in a second. Let's leave the rest for now. Okay, we are going to do this, and even though that's going to be pretty huge, we'll do that out too. What is going to cancel out when in the 15 factorial? Everything from what down? 12 down. So 15, 14, 13 times 12 all the way to 1 is going to cancel with the denominator of 12 factorial.
And then 3 times 2.
And then just 3 times 2.
so therefore we'll cancel the 3 and cancel the 2, and then write 5 in a second.
And now we've got 5 times 7 is 35 times 13. 455 times 2x cubed, 3y to the 12th. Now we just finish it up by doing out the rest. What's 2x cubed? 8x cubed. And now I'm going to get y to the 12th. I'm probably going to need a little more room than that. Okay, what do I have to type in on the calculator now?
3 to the 12th.
Yeah, 3 to the 12th. It's going to be pretty big. It's probably going to be in the hundreds of thousands. I don't think it'll be even in the millions, but it's big. So 531,441. All right, now we're going to multiply what numbers together?
531,441 times 8. Oh no. Right? Yeah.
You gotta distribute that 455.
Yep, 455 times 8. Yep, times.
531,441.
Okay, so we get 1,934,000,000. Which calculator did I use? 445,240. X to the 3rd, y to the 12th. Okay, this is why I would not ask you to do out all 16 terms, because they're huge. But I will ask you for one. What if I said to you, I want you to find the coefficient only? Okay? Just the coefficient of the, let's say, 7th term in, and I'm going to make up a different problem, a little simpler, x plus y to the 13th. How would you find the coefficient of the 7th term in x plus y to the 13th? Yep.
You just do the factorial equation to get the
All right, so what would be your notation for it?
Um,
Yeah, 13, choose 7. You just have to do that out, and that is your answer after you do it out. Now, same problem. What if I said, find the coefficient of the x to the 5th, y to the 8th term? This would be one of your terms somewhere. How could you figure out what term it is?
the y exponent.
You could look. So you could find a pattern looking at the exponents. What if you were confused and you said, you know what, I can't see a pattern?
It's gonna be a 13th row.
Okay, so how many terms would you have if you expanded it out?
14.
Yep, you'd have 14 terms. And now we can figure out, I don't think we need to number them all, but we can figure out where that's going to be. What's the exponent on the x for the first 0th term? 13. What's the exponent on x for the first term?
12.
12, 11, 10, 9, 8, 7, 6, 5. I'm looking for the 8th term. That's where your x to the 5th, y to the 8th. Okay? Or if you just look at the exponent on the y, that's another way to look at it. Okay, so however you want to look at it, you just have to kind of keep it straight. And what would the notation be to find what I'm looking for?
14 over
13.
Yeah, remember, it's always use your exponent. 13, choose 8. And you could figure out what that is. Okay, so you're definitely going to see a question worded like that on the test. Yes?
Why is it the 8th term?
Why is it the 8th term? Because we start out with x to the 13th. Then we have an x to the 12th y. Then an x to the 11th y squared. X to the 10th y cubed, x to the 9th. 8, 7, 6, x to the 5th.
So is it always the exponent on the y?
Yeah, you could look at it that way. Yeah. Great. Any other questions on that? All right. So the homework for tonight, it's on 606. And it's 1, 3 through 8, 11 to 15, 17 to 19, and 21 to 25. Okay, so we'll take a look at that tomorrow before our test. Okay, remember, if you still have a test to make up from last week, tomorrow is it. That's the deadline. If you need for extra help or you're going to be leaving early tomorrow, you're being dismissed, you can come take the test today after school. Tomorrow morning, a couple people said they're going to come. Tomorrow during the day, or during your shop week.
What time will they be good?
On shop week, you can come anytime. Yep, anytime.